Okay, so the rest of the semester is more on, we have a project. You have to choose your project by, so let me write under plan today. So choose the project by next Tuesday. Okay, what project you're going to be working on? That's going to be for 1420. Okay, so choose the project by next Tuesday. There will be up to 2 other written homework. Okay, I'll give you 1 week each. So we got to find a time, find a way to work through that. All right. Let me just not go over the, I think there's a question about the LU algorithm in midterm question 4.2. I thought I would address the midterm questions in a sort of like a, I was going to ask the TA to address all the questions, unless you have a specific question about that. Okay. So let me just give me a second to look at the midterm question 4.2 to see what the question you're asking here. 1 second, I'm having a hard time managing multiple windows, and so problem for part 2. Okay, it's the cost of LU factorization. So I think it's basically the assessing. Let me write a solution because I don't want to spend the time on this one. We'll have the solutions for this thing done shortly, and then we will publish that and we can discuss that at some point. Right, so the question here is mostly looking at the algorithm that was given and analyzing the number of operations. That's the WN is the total number of arithmetic operations in the program, and it's a cubic function. So so you're supposed to get 3 sums, 3 sums here because there are 3 for loops, and those 3 sums then plus maybe 1, and then the second part says that you can approximate those sums. That sums can be more complicated, so you can use integrals to approximate those sums because they are discrete sums, and you can approximate it. And once you do that, you can get the desired answer for that cost of LU factorization. What I will do is to have that publish at some point. Okay. All right. So so mostly, I think what I like to do is talk about another factorization called Cholesky factorization. All right, and then we'll talk about the special matrices. Very special matrices of certain forms that help us solve things more easily. And then finally, the sort of like the a condition number of a matrix. Condition number of a matrix. So condition number of a matrix is going to be helpful for us to know if a given iterative method is going to converge. Okay. So the basic LU factorization, you have gone through that, is the idea that you have given a system X equals B, you would apply a number of operations to A and convert this to some U, X equals B prime. And in other words, at the end, what you have gotten is essentially A is written as an LU product. So you get LU times X equals B. And then assuming UX is equal to some Y, you will solve UX equals Y. Okay, we solve this for, sorry, so the first we solve Ly equals B. We solve for Y. And then once you find the Y, then you can solve UX equals Y for X. So that's the process of solving these things. Okay, I'm going to skip through this one. I don't think we have to worry about this part here. So basically, if you like, you can find the LU factorization. Maybe, in fact, let me just show you a few things about the MATLAB and LU factorization, and the. So let me share my MATLAB screen. Let's see, where's my MATLAB screen here? MATLAB line, here we go. Okay. All right. So using MATLAB, you can find LU factorization easily. So for instance, oops, I think I lost my. So if you type a matrix, so let's say you have a matrix 1, 3, 1, and then 1, 1, minus 1, and then 3, 11, 5. So this is a matrix. And then if you want to find the LU factorization, you can just call LU, which is very simple, LU of A. So it gives you the, this is the lower triangular matrix and the upper triangular matrix. I'm not sure really why it's giving me, so this is clearly upper triangular. This should have been lower triangular. Not sure, hold on 1 second. Let me just look at the LU documentation. LUA is going to give you that. Okay, so maybe. Yep. Okay, I think. All right. Let me go back to the. So clearly, I'm not sure exactly what the issue was, but LUA would give you from MATLAB your LU factorization. Okay. So you could solve a system like this using LU factorization. Okay, so the next thing that we like to consider is what's called the Cholesky factorization. So the Cholesky factorization is all about, given a symmetric matrix. So that's the key thing here. So let's suppose that A is a matrix and A is symmetric. That means A equals A transpose. Given a symmetric matrix, you could do a factorization of A into a product of two matrices. One is called L, which is a lower triangular matrix, and the other one is called L transpose, which is the transpose of the lower triangular matrix. So that becomes an upper triangular matrix. Now, clearly, if you can do a split like this, if you can split any matrix into this form, that means if you take the transpose of that, it gives you L transpose, L transpose. Okay. So if you take using the results, A, B transpose is B transpose, A transpose, this would give you L transpose. In other words, you can only split into this form only the symmetric matrices. All right, so what we mean by symmetric matrices are matrices like this, where you have Aij is equal to Aji. Now, the matrix that's shown here is what's called a covariance matrix. So this is called a covariance matrix. Covariance matrix. All right, so it shows you given 3 random variables x, y, z. So these are all random variables. So they can follow any kind of distribution. Usually for large sets, you would maybe follow a normal distribution. So given 3 random variables, this covariance matrix gives you the relationship between each of these random variables. And the variance of each of the variables is the diagonal element of this covariance matrix. All right. Now, clearly, covariance of x and y is the same as the covariance of y and x. That is how they behave, how they vary among each other, right? So if they have some kind of a relationship, then there'll be some covariance there. Let me just pause here and ask you any other questions. Do you have any questions on this? Okay. All right. So we have this idea that this matrix, covariance matrix, is a symmetric matrix. So symmetric matrices appear in a lot of the applications in real life. For example, numerical solutions to ordinary and differential equations. So if you take an undirected graph and if you represent using a matrix, as you can see, the edges are the elements in the matrix, whether there's an edge or not. So if it's an undirected graph, if there's an edge between vertices v1 and v2 or vi and vj, then the ijth entry would be non-zero, and jith entry would be non-zero because there's a link between the two. So the applications are numerous. Symmetric matrices in real life, a lot of things become very symmetric, and or you can make them symmetric, and so you can solve them easily. Another special type of matrix is called a positive definite matrix. So we call a matrix A is positive definite. So we say A is positive definite. We may have mentioned this before. This means X transpose AX is greater than 0 for all vectors X which is not equal to 0. Right, so they are called positive definite definition. This is the positive definite definition. Now, the way you can think about this is more like if you're just dealing with the number, that could be, you can think of that as positive. So a positive definite means that given, remember that X transpose X is always positive. Okay, so no matter how you multiply X transpose X is always positive. And so you can think of this as a matrix having some kind of positive properties. So what do we mean by positive properties when we have positive properties, right? So let's write down a few things about positive properties. So first of all, a symmetric and positive definite are very important. A symmetric matrix has all eigenvalues real numbers, because a matrix can have either real eigenvalues or complex eigenvalues. What we mean by eigenvalues are the solutions to this equation lambda solution to this equation x equals lambda x. So this lambda can be both real or complex. Lambda can be real or complex. If lambda is complex, we write it as a plus bi, and the lambda bar, which is the conjugate of this complex number, is given by a minus bi. And so it's always the case that the eigenvalues occur in conjugate pairs. So later we're going to prove that this is the case. So for example, if you have an eigenvector V for eigenvalue lambda, which is a complex number, then the V bar would be the eigenvalue for lambda, eigenvector for lambda bar, which is the complex conjugate. So complex numbers always, complex eigenvalues always occur in pairs. All right. Okay, so what we know is that a symmetric matrix has all eigenvalues real numbers. Now, a symmetric matrix, okay, a symmetric matrix has positive eigenvalues, then it is positive definite. All right. Now, if you have any questions, you can unmute and ask me questions. Otherwise, I will assume that you're okay with the lesson. Okay. Now, so we can ask a question like this. So how do we test whether a matrix is positive definite? Okay, how do we test whether a matrix is positive definite? So to test whether a matrix is positive definite, there are a few ways to do it. We can compute all eigenvalues, but this is really hard because computing eigenvalues is not easy. It's a very difficult thing. It's just like computing roots of a polynomial. It's have a very similar flavor, although it's much more higher dimensional. And so computing all eigenvalues is hard. And we can try to check if x transpose AX is greater than 0 for all x which is not equal to 0. That's also difficult because there are infinitely many x's, so you couldn't do that. The third method is to check to see if all pivots, just push this a little bit here, check to see if all pivots, when you're performing Gaussian elimination, are positive. In fact, you might be able to prove this. For example, if you have the matrix 1, 2, 2, 1, now clearly, one of the things you could do is when you're doing Gaussian elimination, you could swap these two and then you get 2, 1. Let's see, like this 2, 1, 1, 2. And now this becomes the pivot. And you perform a Gaussian elimination. For example, you multiply row 1 by -2 and add it to -1/2, I guess, right? -1/2 and add it to 1, which will give you 0 here. -1/2 and add it to 1. So this would be like, this doesn't change. And 2 minus, let's see here, 2 minus 1/2. So that's going to be 3/2. So now the next pivot is this one, and they're all positive. So you can assume that you can determine that if all pivots are positive, this matrix here is a positive definite matrix. So this is probably the easiest way to check whether something is positive definite. As you will see, there are a lot of interesting features about positive definite matrices. Okay. All right. Okay. So let's talk about the applications of positive definite matrices. Okay. So first thing I like to define what's called a quadratic form. So quadratic form of a matrix. In all these cases, I'm looking at a square matrix. Okay, a quadratic form of a matrix is a function from set of vectors in Rn to some one-dimensional number R, such that f of x equals x transpose ax. So in some ways, this is like x squared in our one-dimensional form. It's like x squared. So if you imagine that A is a 1-by-1 matrix, you're really looking at something like x squared, because x transpose x would be like x squared. All right. So, but in higher dimensions, this is called that's the quadratic form. Get some space here. Okay. And we can assume that A is symmetric. We can assume that A is symmetric. But if it is not symmetric, we can always find an approximation to A by taking 1/2 A plus A transpose. All right, assuming that you don't have a lot of weird kind of entries here, right? So because this is a symmetric matrix, and sometimes even if you don't assume that A is roughly equal to that 1/2 A plus A transpose, that matrix is symmetric, and you can do a lot of things that you want to know about A by looking at A plus A transpose. Okay. So we can say a symmetric matrix is positive definite if and only if its quadratic form, which is given above, is strictly a convex function. Convex function. So what we mean by a convex functions are really important, because if you just think about something like this, that is a convex function. Okay, this convex function has a minimum. And starting with a reasonable place, you might be able to approach that minimum point. Okay, so one definition of convex function is if you take any 2 points on the curve, and if you join them, either the convexity or the concave up or concave down is on one side of that line. Okay, so convex functions are really important. So this quadratic form, if you plot it in that higher dimension, we cannot really plot it, but if you do plot it, then it's a convex function in that higher dimension. So it helps us minimize functions that involve more than one variable, multivariable functions that you can minimize. All right, let me see whether. Okay. All right, so the positive definite matrices, like if A is positive definite, and because if A is positive definite, then we know that X transpose AX is always positive. So your numbers are above, they're positive, right? Something like this, where the function is positive function, greater than or equal to 0. So if A is positive, we know that X transpose A, or the quadratic form, is a positive function. And therefore you can, according to this, it says symmetric matrix is positive definite if and only if its quadratic form is strictly a convex function. All right. Okay, next I want to talk about least square applications of positive definite matrices. Okay, least square applications of positive definite matrices. Now, here's a theorem. If A is any real matrix, then A transpose A, let me write it like this. A transpose A is positive semi-definite. Okay, the definition of positive semi-definite is essentially x transpose AX is greater than or equal to 0. All right, so it could be 0 there. So to prove that, we can always show this. The proof of this is going to be we take x transpose this matrix here, which is A transpose AX. And you can write this as AX transpose, because AX transpose is X transpose A transpose times AX. And this is really the dot product of AX and AX and AX. And dot product of AX is always greater than or equal to 0. Now, if AX equals 0, that means X is in the null space. It's possible. If X is in the null space of A, then AX can be 0. So more importantly, sort of like solving a least square problem. So solving a least square problem is something like this. Given a set of points, this occurs in a lot in regression and other areas, right? We like to find, let's say you have given endpoints, maybe you can find some curve that goes through all of that, if it's possible, right? It might not be possible. Now, if you really have endpoints, x1 through xn, and then you have their y coordinates, y1 through yn. This is all only in one-dimensional things, right? Two-dimensional. So you could find, if you assume that this equation is of the form that a0 plus a1x plus a2x squared plus an xn, and you can plug in these points x1, y1, x2, y2, x3, y3, and if you do that, you can end up with a system of equations ax equals y, and if you solve for I mean, I think in this case, A is the matrix which has the coefficients, right? That's the coefficients, and then so you could find a solution for that. In fact, when you talk about AX here, it's really the matrix of 1x, x squared, x to the n. So essentially, it would be like 1x1, x1 squared up to xn squared. No, x1 to the n, sorry. x1 squared, x1 to the n. And like that, so you have 1, here you have xn squared, and xn to the n. So that is your, and then you can find a naught a1 to an, and then you have your y's. You solve and find this. Right, you can find this, but that's not very practical. So you have to, you know, it's a lot of equation solving to find the perfect fit through this. Now, typically, what you do is you find, given a set of points, you try to put either curve or quadratic form or cubic form or linear form. That is as close as possible. So essentially, your goal is to minimize the error from your estimation, because your estimation is the curve. So you want to minimize these errors. So these are all errors. You want to minimize them. And that's really the goal. Okay. So to state this problem, you state it like this. You want to minimize the difference between the difference between AX and B. If you're trying to solve this problem, you want to minimize this 2 norm to find the minimum solution, the solution that will minimize minimize this, right? And so basically, when you think about ax minus b, the norm, which is ax minus b transpose times ax minus b. And if you expand this, you will get x transpose A transpose minus B transpose, and then ax minus B. And if you multiply this out, you're going to get x transpose A transpose AX. And then you will have B transpose AX minus X transpose A transpose X transpose A transpose B plus BB transpose. So that's the quadratic form you get. And then if you take the derivative of that, or the gradient, if you take the derivative of that with respect to x, where x is the variable, you're trying to minimize the quantity subject to x. Essentially, you can think of this as a quadratic form. So you can think of this, you can think of this as x squared. So if you differentiate x squared, you're going to get 2 x A transpose A. You'll get that. And then both of these will give you, because you have only one x here, or x transpose the same thing. So you're going to get minus 2 A transpose B. In fact, both of these things, you could rewrite them in some kind of transpose form. And if you set it equal to 0, you solve for x. So then you have this system. Actually, this should be that. You have the system A transpose AX equals A transpose B. So this is a very important thing that we just did. Basically, if you have a system which is AX equals B, let's suppose that's overdetermined, so we don't have a unique solution. And maybe it's not a rectangular system, there's no inverse exists. What we can do is we can multiply both sides by A transpose. So you have X equals B, and you multiply by A transpose. Now this becomes a square matrix, and perhaps with the inverse. So you can find the solution to that to be A transpose A inverse times A transpose B. Okay. All right. Do you have any questions here? Pause just a little bit. Okay, doesn't look like you have questions, so let's just keep going here. Okay, so what we did so far is to kind of show that positive definite matrices such as A transpose A is really the least square solution. So when you're trying to find the least square solution, you have this as the least square solution to a set of points, right? It finds the solution that minimizes the sum of the squares of the errors, right? Okay. So the Cholesky process, which is essentially given positive definite matrices, you could find a factorization, L and L transpose, where L transpose is the upper triangular part of L. Okay, it's also possible that in literature you might find that A can be UU transpose. So that's more like U is an upper triangular matrix, and U transpose is a lower triangular matrix. So the same thing can be applied either, you can say, given a symmetric positive definite matrix, you could write A as a product of lower triangular matrix and its transpose, or an upper triangular matrix and its transpose. The advantage of doing this compared to A equals LU is that you don't have to find L and U both. So you only have to find L and then you're done. So you might imagine when you have a positive definite symmetric matrix, the amount of work you have to do is half the work compared to doing LU factorization. Okay, the amount of work is half the work compared to that. Okay, so mostly, so to give you sort of like an example of this kind of factorization, it would look something like this. This is one of the examples that I have. So in this case, you're given a positive definite and symmetric matrix. And so here's the lower triangular part, and this is the L transpose. Now notice that the column here is the row there. Okay, so that's the sort of the relationship. The nice thing about being able to take A, and so if you have a system like A equals B, and we know that A is a symmetric positive definite matrix, you could write this as L transpose X equals B, and then similar to the process that we use for LU decomposition, you call L transpose X to be Y. So we take L transpose, so then we have, if you call that Y, then you have Ly equals B, that we solve for Y, because it's a lower triangular matrix, so you can easily solve for Y. And then you have to solve L transpose X equals, we want to solve this for X. Okay, so that's essentially the same process as the LU decomposition. Okay, so let's take a look at the next one. Next one is proposition here. Okay, so this is a result on a positive semi-definite matrix. Now, positive semi-definite means, if you recall the definition, X transpose AX is greater than or equal to 0 for any X. Okay, for any X, in this case, we can say any X is fine because we have the greater than or equal to 0. And what this says is that given a matrix A, which is an M by N matrix, and the matrix A transpose A is positive.
Sorry, Professor, I don't see any screen.
Yeah, go ahead.
I don't see your screen. Are you still sharing?
Oh, wait, I'm not sharing. Oh, maybe I did. Okay, do you see it now?
Yeah, thank you.
Okay, thank you for letting me know. Yeah, hopefully I just lost it, right? I was just trying to, yeah, okay. So I think that what this result is saying is that given any rectangular matrix A, the matrix A transpose A is positive semi-definite. Okay, so how do we check that the A transpose A is positive semi-definite? What we can do is we can take X transpose AX, because that's the general method of checking whether something is positive definite or positive semi-definite. And then you can write this as X transpose A transpose times AX. And you can write this as AX transpose AX, because X transpose A transpose is AX transpose. And clearly, when you take this, like the dot product between AX and AX, and dot product is always greater than or equal to 0 with the same thing there, right? Or you could just say this is also the 2 norm squared, right? 2 norm squared. Now, the second part says that if A transpose A is positive definite, so you have positive semi-definite, now it says positive definite. That means X transpose AX is strictly greater than 0, exactly when the columns of A are linearly independent. Columns of A are linearly independent. So if you, so how would we prove that? Okay, so let's assume that columns of A are linearly independent. Okay, let's assume that columns of A are linearly independent. Okay, so we know that if we're trying to prove that A is positive definite. Okay, so we will prove this by contradiction. We will prove this by contradiction. Okay, if A is positive semi-definite, right? Positive semi-definite. Okay, then we know that there exists some X which is not equal to 0, such that X transpose, X transpose A transpose AX is equal to 0. If there's some kind of, if A is positive semi-definite, that's got to be some vector that'll make this 0. But this would imply that the norm, the 2 norm, would be 0. All right, and that kind of contradicts that because if that it could be it's like for example, if AX equals 0, okay, this implies that columns of X are linearly dependent. Okay, if you can write X equals 0, and then the columns of X kind of depend on each other, right? Because you could write the columns, because there's some kind of a linear relationship between the columns of A. If you write the columns of A as column 1, column 2, and column n, and some X here, x1 to xn, and if this is equal to 0, that means, you know, there's some relationship between these columns, right? So the columns of X are going to be linearly dependent. So that contradicts the sort of the independence of the columns of A as given. All right. Okay. So in other words, this is a good result here, which says that it's positive definite if you know that the columns of A are linearly independent. All right. Okay. All right, let's go to deriving the Cholesky factorization. Let's do that. So how do you derive the Cholesky factorization decomposition for a given matrix? So the way you can think about this is, let's say you're given an A, and I want to factor this as L and L transpose. And we assume that A is definitely symmetric, the way it's given. If I'm able to factor like this, L transpose, it's symmetric. And we can also assume that A is positive definite. Okay. So the basic idea is that given the matrix A, we have A11. Oh boy, hold on. Second, I'm having technical problems here. Okay, given the matrix A11, A12, A1n. So if you take that matrix and if you write it as L11, L21, L22, Ln1, and Lnn, these are all zeros. And then this side you have L11, L21, Ln1, L22, Ln2, and so on, right? So we have this form. Now, so finding a solution is quite easy. For example, if you take this entry, A11, that's going to be the product, that entry is the product of the first row and first column. So you have L11 squared. All right. Now, that implies that L11 is the square root of A11. So one requirement for positive definite is that all the diagonal elements have to be positive, right? And actually we can prove that. So the A11 has to be greater than or equal to 0. Otherwise you cannot take the square root. Now, if you take the first row and the second column, you get first row, second column, you get A12, I'm sorry, A12, right? First row, second column. What you're going to get is L11, this is all zeros, right? So you have L11, L21. And because we know L11, we can find L21 to be A12 over square root of A11. All right, so here we found, so what we are finding is now we're finding these entries, right? We're finding this one. Oops, that's too big. Second here. Yeah, we're finding these entries. Okay, so we can, so when you compute the Cholesky factorization, notice that the one that was computed in the previous step becomes helpful in the next step to compute L21. So like that, you can just continue to compute Ln1, okay, by looking at, one second here. Yeah. Okay, so if you keep writing the last element, which is A1n, which is the first row, that is L11, all zeros here, right? And the nth column, which is Ln1 to Lnn, which just gives you L11, Ln1. Right, so I could easily find the elements in that column. So you can imagine that the process, you can easily compute these things without much of a problem, right? So by using first row of A and all the columns of, first row of A, we could compute all the first column of L. That means you know the first row of L transpose, right? So we find two then. Okay, so here this is a Cholesky factorization. I won't go into that. Maybe you can try this as an exercise, like I did here. So you could try this as an exercise. You could also find this using MATLAB. Let me see. I'll show you how. Share my MATLAB screen. Oops. Okay, so let's type in. Okay. So 36, 30, 18, 30, 41, 23, 18, 23, 14. And then let's see, I think it's CHOL, Cholesky factorization. So this is sort of the documentation. It just gives you various things of. So what this does is to factorize a symmetric positive definite matrix A into an upper triangular. So in this case, you're going to get an upper triangular matrix, not the lower triangular, like I did there. So if I do like chol A, all right, so it gives you the upper triangular matrix, right? So let's say I equate this to U. All right, and then I believe that, let's see which way I go here. U transpose U, probably not. Okay, I forgot how to multiply. But if you multiply the U transpose U or UU transpose, you're supposed to get the original matrix, this one matrix here. Okay, so that's what it is. Okay, let me switch back to my. All right. Okay. So one of the things I might ask you to do in the next assignment is to implement a Cholesky factorization. Here's the algorithm. I'll share this with you. So you take this algorithm and implement it. And there are a few things that are important in this algorithm. I think you saw me doing this by hand. So basically what this is trying to do is to given a matrix C, it will try to factorize that into L times L transpose. And we are going to check whether C is symmetric and positive definite, because if they're not, you won't be able to do this. And the algorithm given here is very interesting because it destructively replaces C with L. So it's destroying the original matrix and slowly make it L. So at the end, you end up with L. You can save L if you want. So actually, in this case, you start with this assigned C, and then you slowly make it a lower triangular matrix and return L. So maybe one of the things you could do in the next homework is to evaluate something, implement something like this. All right. So essentially, Cholesky factorization, you can see this as the end result of a sequence of transformation to a lower triangular form. So just as we thought that the U matrix in the Gaussian elimination is the end result of a sequence of transformation to the upper triangular form. So again, wrapping things up, you're saying once we have the Cholesky decomposition, we can solve systems of equations Ax equals B using forward and backward substitution. And a few advantages of Cholesky decomposition. It has very practical properties because it can apply to positive definite symmetric matrices, one thing is it takes only half the memory to store L, because we are only doing L, not L and U. So it takes only half the memory. So you're cutting down the requirement for the memory from n squared to n squared over 2. And also in terms of steps, it's also taking half the steps of LU decomposition. It's still the same level of complexity, like n cubed, but it's just give you 1/2 of that. So that is good. Okay. All right, so this problem, you can probably do this as an exercise. I'll share these slides with you at the end. Okay, there are really, I think again, I'm emphasizing Cholesky quite a bit because of the common form that you can find this in many real situations. And one of them is essentially the covariance matrix, like we saw. Okay, so the covariance matrix, and given the covariance matrix, that's the covariance between the relation between, say, 3 variables here, and what's given here is the variance. And if you take the square root of that, you get the standard deviation. And and you can find the correlation coefficient. And correlation is essentially, you can derive that from the covariance matrix. That's the correlation coefficients, which are always between -1 and +1, right? This is always between -1 and +1, all of them. And your correlation of a variable with itself is always 1. And it's sort of like a standardized form of covariance. It's called the correlation matrix. And they are very important in data science and other areas. So one application of this Cholesky decomposition is what's called the Monte Carlo simulations. The Monte Carlo simulations are very common in data science because if, let's say, you have a bunch of variables, let's say x1, x2, x3, let's say, you can have like n variables, n random variables. So you have n random variables that are seemingly maybe uncorrelated. So they may be uncorrelated, right? But in order to study properties about these things, you like to have them, some kind of relationship between them. And you can also assume that these are all coming from some kind of a normal distribution. Okay, you can assume that there are values between 0 and 1 coming from a normal distribution. So one of the Monte Carlo simulation is all about how to create a simulation, because we can't really do this in real life. So we simulate all these random variables and we run them through many samples. We assume that all of the random variables follow a normal distribution, but we would like them to be related somehow, related. If they are not related, then your covariance matrix is not interesting. It's a diagonal matrix. And so you like them to be related. And so one of the ways that you can make them related is that, so given a covariance matrix, you find its Cholesky factorization, L times L transpose. And so given this vector, if you call this the big vector X, and then if you apply to vector X, one of these lower triangular matrices, you get another vector Z, and this C is the related variables. So Z is the related variables. Okay, these are related variables. These are uncorrelated. Right. So basically, we would like to work with that because of its Z. And the interesting thing is that the covariance matrix of this set of variables is also C. You can prove that. Okay. So you start with a covariance matrix which is of uncorrelated random variables, and you find the Cholesky decomposition. And then if you take the original set of uncorrelated variables and multiply that by the L, you're getting a new set of variables, Z. Those are correlated variables. And it turns out that the covariance matrix did not change. Although the matrix, so that's one of the interesting things. I'll probably describe this. This is sort of like a covariance matrix of what you're seeing here is things that are uncorrelated turning into correlated kind of a form once you apply this thing here. Now, there's a lot of, I teach data science, so there's a lot of interesting applications in data science for this idea. Okay, so linear algebra and matrices are quite important in data science. Okay. All right, so the next topic. Yeah, so the next topic is this topic here. So we're going to look at special types of matrices. So there are three types of matrices that are very common in many of the applications. So if you take a differential equation, use finite differences to come up with a matrix system, you might get a very specific type of matrix. Like, for example, covariance matrix is symmetric, and positive definite. And oftentimes you also get what we call banded matrices. So they have a band. They have very special form. More like you're getting these kind of things from things like this: x1 plus x2 equals, say, b1. And then you might find 2x2 plus x3 equals b2. And then you might find x3 plus x4 is equal b3. Now, if you think about that, what I'm doing now is that essentially I'm creating a banded matrix. And what this shows you that is that the variables that are close to each other, x1 and x2, are related, but they don't have any relationship to perhaps, x1 is related to x2, or x2 is related to x3, x3 is related to x4 in some manner. And but oftentimes you find these kind of systems in real life, and they end up with a sort of a band matrix. So the nice thing about the band matrix is, if you have this matrix, then you could apply very special methods to solve that. So you probably don't want to apply something like LU factorization, because if you take something like this, and you can mess it up if you do LU factorization. But there are other methods that can be applied. And then the third type of matrix that's very common in applications is called the sparse matrix. So sparse matrix is you have a whole bunch of stuff here, here, here. Now, very important example of a sparse matrix is that user rating matrix in data science. If you take a user rating matrix, so certain users may rate only few items, and so on. So you can see a sparse matrix in a user rating matrix. So that's a sparse matrix. And then what are the properties, and how do we store these things? How do we solve these things? Now, in this case, you might be interested in knowing, well, user did not rate, this movie, right? So this movie. So let's say, actually, this is the movie. Let's call this movie. Okay, so what you're writing is the rating, right? So the user might give rating like, okay, 5 for this one, that movie, movies are 1 to n movies, m users. So you have an n by m matrix here. Either way is fine, right? And so user 1 may have rated movies, a few movies here, but you might wonder how would the user rate this movie because if I want to recommend that. So usually, typically what you have to do is to find, if this is the user vector, you find another vector which is similar to, so similar means that they kind of go in the same direction. Okay, that's what you're looking for. And then if this user has given 4 for that movie, maybe you might consider giving something close to that for that user if they are similar. Right, so for those kind of matrices are often sparse matrices that you get. Okay. So next thing is the linear systems and banded matrices. So we can say that, just to give you a definition, a matrix is banded. Matrix is banded if Aij is 0 for I minus j less than greater than p. Okay, and then we call p is the bandwidth. Okay, p is called the bandwidth. An example of that would be something like, let's say you have a matrix with 3 bands. One, the main diagonal, and the next one. So in this case, p would be 3. All right, so what it says is that the difference, the index difference between I and j greater than p is 0. That means these are all zeros here. Okay, so when you have banded matrices, they are easy to solve. And there's an interesting, again, like I mentioned before, that you might find a system where x1 and x2 are related, x2, x3, x1, x2, x3 is related, something like this. In this case, if you look at this matrix system, and this is very common type of a matrix system that you might find when you try to model a system. Okay, so you might end up with this and you're looking to solve for x1, x2. So you might ask the question, well, what should I do with this matrix A? Should I take the LU decomposition? Should I do the Gaussian elimination? What should I do to solve this? You don't do that because it's a tri-diagonal system, and therefore you might be able to use better methods to solve it. What do we mean by better methods? So let's take row 1 and this one. So if you look at row 1, you get b1x1 plus c1x2 equals d1. All right, so you get one thing there. From that, you can say x1 is going to be then some kind of, let's just make it more like alpha 1 x2. So in other words, I'm expressing x1 in terms of x2. Okay, so and alpha 1 and alpha 2 you can compute. They are based on b1, c1, d1. You can compute them. Now, if you look at row 2, and what you get is a2 x1 plus b2 x2 plus c2 x3 is equal to d2. By using that, you can find x2 in terms of x3, because we have, so we can solve x2 in terms of x3, right? So x2 is going to be alpha 2 x3 plus b3, b2. All right, because it's just a substitution, right? Because we know x1, we can express x1 in terms of x2, and then x2 in terms of x3. And if you keep going like that, at some point, you're going to express xn in terms of xn minus 1 is going to be some kind of alpha, I guess, n minus 1 xn plus beta 2, right? So the last element, if you look at the last element is this and that you have am x1, bm x2, and then you could solve it and start to go backwards because you have a relationship. You can do back substitution starting from xm to find all the values there. So what you have is sort of like a forward substitution algorithm, and then the backward substitution algorithm to find the things. And so without finding Gaussian elimination or LU decomposition, you are able to solve that. Okay. All right. Okay, I think we are running out of time. So what I will do is, so for Thursday, I'll create, there are a bunch of other things that I wanted to discuss, but I will probably make a video and send it to you. And also I will send you a video of the iterative methods for solving AX equals B. And so that's going to be our next kind of next topic there, the iterative methods. And one of the projects that you're going to be doing is based on the modified iterative methods for Gauss-Seidel and Jacobi methods. Okay, so let me just give you a few minutes to ask any questions. Actually, in fact, you have some of the questions here. Yes, so if you use the LU factorization on a symmetric PD matrix, yes, you can still get the LU factorization, so it's not the same thing as Cholesky. So you have to make an effort to get the Cholesky factorization. So you're not necessarily going to get the LU factorization. It's not the Cholesky factorization. But to get the Cholesky factorization, you must have a symmetric positive definite matrix. And LU factorization, you can get it for any matrix. Remember, the factorization is not unique, okay? So it's not like prime factorization. You can take a matrix and factorize in a lot of different ways. There's another factorization that we'll talk about called QR factorization. That's also lead to a lot of interesting applications there. What are the other questions? Okay, are the project ideas only the 3 on the project document? I haven't been able to come up with a 4th project, which I want to do. Maybe I'll try to do it this week. I like to give you 4 projects. I did the 3rd one. So the first one is the modified Newton, which is based on Professor Kalantari's new paper. It just came out. So it's a new algorithm. I haven't studied that algorithm myself, but he tells me that it can be implemented. And the nice thing about that algorithm is no matter where you start, you converge. The second project is the modified iterative method, which is one of my papers. So you will try to apply that. The third project is essentially comparison of iterative methods. So we have Gauss-Seidel and Jacobi. We'll talk about that next week. And what's called this SOR method. And there are a few other methods that what I would like you to do there is to really play with, write programs to compare and to compute, for example, eigenvalues, because computing eigenvalues is not trivial. Okay, you can plug it into a matrix, but I would like you to sort of, write a program to do it using methods such as power method. Okay, so power method for finding, for example, the largest eigenvalue, right? Okay. And so I will come up with, I'll think about fourth problem. I haven't, I looked at few examples, but I haven't found anything that I like yet. Any other questions?
I have a question about the Cholesky factorization thing.
Mm-hmm.
So, if you use LU decomposition on a symmetric positive definite matrix, do you get the same answer as if you do Cholesky factorization?
No, I don't think you are going to get the same answer.
Okay.
You're still going to get an LU factorization for that matrix, okay? So Cholesky is very special. And to apply special to a, that means you've got to start with a symmetric positive definite, right? Yeah. So like I said before, the factorization of a matrix is not unique. So you could have a lot of different factorizations, right? Even if you take, there's another version of Cholesky factorization, which is in UU transpose. That's upper triangular forms. There's no difference between the two, LL transpose and UU transpose. They're two different things, but different matrices, yeah. Any other questions?
Thank you.
Yeah, thanks. You can unmute your microphone and ask me a question if you like. Would you like, anyone want to comment about the test? We haven't started grading, but would you like to, for me to consider certain things? You can always also email me if you don't want to say anything right now.
The one thing I would like to mention is on that last problem, the MATLAB implementation.
Mm-hmm.
I don't know if anybody else had the same issue, but I couldn't run any of the like higher size matrices in a reasonable time.
Yeah, I think someone mentioned maybe 10,000. Did you do 10,000 by 10,000?
I got to 1,000, and then I did some math on the back of the sheet of paper, and it was gonna take something like an hour and a half to run the 10,000 one.
Okay, that's good. Did you submit that, the analysis?
I couldn't get MATLAB to run on my machine, so I was using the browser one, and it was timing me out after 10 minutes, so I couldn't get that to work.
So was it, it was an n-squared algorithm, right? Or was it quadratic?
N-cubed, I think.
N-cube, yeah. That's why I think, 10,000 to the cube is quite big.
It's big, yeah.
Yeah, it's not going to do it. But in fact, a nice thing would have been to really, do some experiments. And if you didn't know it was n-cube, could you figure that out by running it for different sizes, right? Like doubling the size or something. Right, that would have been a good experiment. Anyway, yeah, don't worry too much about that. I think we understand the MATLAB limitations. That's okay. Right. Ideally, you would implement this in Python or something and, have some kind of memory management. Still, your runtime is runtime, so you're not going to get anything fast. Okay. Yeah, okay. Any other questions? All right, so Thursday, as usual, to be, I don't know how things are going for you. I think, I really don't enjoy this format at all. It's just, it's like talking to a computer, and, it's really hard to perform in this one. So let's, we'll get through this, but I think maybe, spending Thursday looking at some videos and stuff like that would be fine. Okay, rather than going through this twice a week, it makes no sense. like taking TOEFL speaking. Yeah, that's right.
One more
Okay.
thing. When will you post the third assignment?
That should be sometime this week. Okay. This is the
Okay,
11th week, I think. Is it the 11th or 12th week? I'm sure. I think 11th, right? Yeah, I will get that this week. Any other questions? Otherwise, we can wrap things up, and I'll see you next week. All right. Okay. Bye-bye.
Thank you. Bye.
Bye.
You.